So I got response from a lot of people, and I think my audio is fine. So let's get started with the training session for construction stage analysis. The first session that we did was for the general introduction to Midas Civil, how to do the modeling, how to define the loads, how to define the supports, and now we'll be talking about the construction stage analysis. In this training session, I'll be modeling a simple bridge, and I'll be modeling the construction stages of that bridge. So let's get started with this training session. These will be the contents of my training. I'll be talking about the modeling features for construction stage analysis, and then I'll be talking about the construction stage analysis control, and finally we'll discuss the results pertaining to construction stage analysis. So first of all, why do we need to do construction stage analysis? So I've listed out some important reasons why do we need to do construction stage analysis. Of course, you guys might be knowing much more than that, but just to sum up, the construction sequence may lead to critical forces which may lead to shear or texture failure when the construction is being carried out. The long unsupported cantilever sections, if you are going for a balanced cantilever type of construction, the long unsupported cantilever sections may induce forces which may be substantially different from those in composite structure. As you can see in this example, I hope you guys can see the picture. You can see that when this arm of the balanced cantilever is in a cantilever position, then it will have very high negative bending moments, and this stage might be critical, and that's why we need to design the section that it can take these negative moments, and that's why we need to do construction stage analysis. Also, apart from the force effects, sometimes we need to consider the time dependent material properties so that we can consider how the creep or shrinkage changes in different construction stages, and we might have to do erection engineering to consider creep and shrinkage accordingly. So this is how we perform the construction stage analysis in Midas Civil. This is a simple flowchart which demonstrates how to do construction stage analysis in Midas Civil. So first of all, we will model the structure. After the modeling of structure has been done, we'll define certain structure groups and we will assign the structure inside the structure group. Then we will define the load under the load groups. Then we will define boundary under the boundary group. Then we will generate the construction stages. Then we will define individual construction stage, that which element has to be activated, which one has to be deactivated. And finally we'll set up the construction stage analysis control so that we can see what specific results do we want, what factors should be considered while the analysis has been performed for construction stages. So this is how the construction stage dialog box of Midas Civil looks like. I'll be shuffling between Midas Civil and the presentation from time to time so that I can tell you where you can find these dialog boxes. So let me take you to Midas Civil. So as you can see on your screens now, this is the work window of Midas Civil. And on the top we have the menu bar. If I want to define the construction stages, I have two options. The first option is I can go to load and I can go to construction stage analysis data and I can go to define construction stage. Once I click on this option, we will see that there are certain construction stages that will be defined. Let me just delete all these construction stages and I'll show you how we can add a construction stage. So here I'm deleting all the construction stages. So if I want to add one more construction stage, I'll click on add. Simply I will give it a name and then I will define the elements that have to be activated, the boundary that has to be activated, and the loads that have to be activated in this construction stage. The second option to invoke this dialog box is to click on this option, which is right behind the wizard option here. If you click on this option, you will quickly get the construction stage definition dialog box and you can define the construction stage. So once you are proficient with modeling, you can just use the quick selection tools with the help of which you can define certain things. Now let me talk about this dialog box briefly. What is it about? So as you can see here, we have three different tabs in the define construction stage field. So as you can see here, we have three different tabs in the define construction stage field. The first tab is element tab, the second tab is boundary tab, and the third tab is load tab. Within a construction stage, you can either activate the element or deactivate the element. You cannot do both things simultaneously. So similarly, you can have activate a single boundary. Either you can activate it or you can deactivate it in a particular construction stage. But as far as the load is concerned, you can activate the load at multiple steps in a single construction stage. So as you can see here, this is a chart which describes what we can do in a single construction stage. So here I have a construction stage for 20 days, and as you can see, the construction stage duration is 20 days. I have a first step and a last step. In the first step, we can activate or deactivate element, boundary, and loadings. In an additional step, I can activate or deactivate the loadings. But in the final step again, I can not touch the elements or the boundary, but the loads can be activated. So in the first step, you can only activate boundary, elements, or loads, but in the subsequent steps, you can activate or deactivate the loads as and when you require. So first of all, as I said before, we need to define groups when we want to perform the construction stage analysis. Now the question is, why do we need to define the groups? We need to define structure group, boundary group, and the load group, and the importance is only the structure groups, load groups, or the boundary groups can be activated or deactivated in a construction stage. Let's say you model the element and the element number is element number 1. You cannot activate that element in a construction stage. So as you can see here in this model, the element number of the pairs are 73, 76, 74, and 75. Now in first stage, I want to activate these 4 elements. But if I see the construction stage definition dialog box, we cannot see any element because we haven't defined any group. So the importance of group is, if you want to activate a load, an element, or a boundary, you need to activate the group in which that element, load, or boundary is present. In MIDAS Civil, we have one more option to define the tendon group. But tendon group is not used to activate or deactivate a tendon. It is just used to see the results of a certain number of tendons together. Now I'll take you to the program and I'll show you where you can define the groups. So this is the work window, as you can see, and on the left hand side is the works tree, and the works tree, as all of you know, it shows all the definition that you have done in the model so far. If you go to the group tab, this is where you can define the groups. As you can see, you can define structure groups, you can define boundary groups, you can define load groups, and you can define tendon groups. I have defined certain groups in this model already, but I'll be defining new groups so that I can show you how the groups can be defined. So this is the balanced cantilever model, and today I'm going to show you how to model the construction stages of a balanced cantilever bridge. And these are the stages. In the first stage we have the pier and the pier table. Then we keep on adding the segments on the left and the right arm of the bridge, and this is how the construction is going on, and finally we get the whole bridge. So this is something we are going to simulate today in the construction stage analysis online training. So first of all, let's talk about the element activation and deactivation. In element deactivation or activation, we should activate only those elements which will become structural components in a construction stage. By structural component, I mean that when the element starts to take its own load, or when the element starts to take the load of the other elements, then it has become the structural component of that bridge. For an example, if you see the cast in situ balanced cantilever bridge condition on the right hand side in the picture here, the concrete inside the scaffolding or the formwork is still wet. It doesn't add to the stiffness matrix of this bridge. It doesn't add to the strength of this bridge. So we will not activate such an element in the construction stage. Although it has been casted, the concrete is in place, but the concrete has not hardened We will only activate this element when the formwork will be removed and the element will start to take its own load, or the load of the surrounding elements, or the load of the scaffolding, or the man who are standing on the top of bridge for further construction. So, to sum up, the elements which still have the scaffolding or the wet concrete should be included as weight, and they will not contribute to the stiffness of the structure. And this is how the elements are activated or deactivated. So as you can see here, I want to activate element number 17 and 25 in construction stage 3, let's suppose. So first of all, I will model the elements. I will put the element in a structure group, and then I will assign the structure group in the construction stage 3. Now I'll do the same thing in the model that we have, so that we get to know how the construction modeling has to be done. So this is the bridge that I have. I want to include the pier table and the piers in stage 1. So I'll define a group, let's say pier, and then I'll define one more group, let's say it is pier table. To define the group, we have two options. Either we can right click and click on new, and you can rename this group, or you can click on new ... and then you can create multiple groups at the same time. So let's say I want to create the segment groups from 2 to 10, then I can just write 2 to 10 here, and the segment 2 to 10 groups will be created. So as you can see here, now I have created automatically the segment 2 to segment 10 groups. Up till now I have just defined the group. Now I'll assign the structure, the elements inside the groups. For that I will select the elements. So here I have selected these elements. First of all, I just need the pier. So I just select the pier elements, and I will put them into the group, the structure group pier, by selecting the group and keep holding the left mouse click and dropping on the model. So in this way I have assigned 8 nodes and 4 elements into this structure group. Now I'll do the same thing for the pier table, as you can see here, and I will do the same thing for segment 1. So this is how I have defined 3 different groups: group 1 pier, group 2 pier table, and group 3 the segments. Now I want to create a construction stage in which I will activate. In the first stage I'm going to activate the pier plus pier table, and in the second stage I'm going to activate segment 1, and then we will activate the subsequent segments. So I will click on this option to obtain the construction stage definition box, and I'll define first construction stage. So I'll give it a name, stage 1, and let's say the duration is 30 days. I will activate the pier with certain age. I'll be talking about the age in details in subsequent slides, but as of now we have to define an age. Why do we need to define the age? I'll tell you later. And this is how stage 1 has been defined. Now I'll add the second stage, in which I will activate the segment 1 with a certain age. If I see the construction stages now, this is my stage 1, in which we have the pier and the pier table, and in stage 2 we have one more segment on the left and the right of the pier table. So I followed the same approach as in the presentation. You can see I selected the elements, I put them in the structure group, and I activated that structure group in the construction stage. Now let's talk about what this age is. A lot of people are confused about what should be the age of the elements, what should be the activation age of the elements. So today I'll be discussing what this age means. As you can see, the description is define age of the element at the time of activation used in determining the time-dependent material properties. As we know that if we want to determine the creep effects on the concrete, we need to know the loading age. In a way, this age is the loading age of that element. But how to calculate that loading age? So this is a simple example that I have provided. Let's say we are going to construct a composite steel plate girder bridge. Now in a steel plate girder bridge, the first stage is installation of steel girders. The second stage is we pour the wet concrete on the top of the steel girders, and then with due course of time the concrete hardens. And then we remove the scaffolding, the formwork, whatever we have, and then we let the structure take its own way. So here you can see that in construction stage 1 I installed all the steel girders, and on the 10th day of construction stage 2 I casted the deck. That means I poured the wet concrete onto the top of the steel girders and I let the concrete be there for 20 days, and I removed the scaffolding or I removed the formwork after 20 days. So the age of concrete becomes 21 days. So the concrete starts taking its own load after 21 days, and this will be the age that will be used to activate the deck element here. So when you activate the deck element for this type of construction, you will specify the age as 21 days. Now let me take one more example. Let's say you are dealing with the precast members, and you cast the members in the site and you bring them, you cast the members in the plant and you bring them to the site and then you install them. Now how to calculate the loading age in this scenario? In this scenario, it's very simple again. The day you casted the member, start from that day to the day when you installed the member, and it will give you a clear picture of what should be the loading age. So let's say at t equal to 0 we casted the element in the plant, and then at t equal to 10 days we set up or install the element in the bridge. So the loading age will become, or the age will become 10 days. So this is the concept behind the age. The second thing that you can see here is when you deactivate an element, how to redistribute the force. Once the element is there in the bridge, it will take certain loads, and if you remove that element, if you deactivate that element, the forces that were taken by the element should be redistributed inside the structure. And here you can define the percentage of forces resisted by the element to be deactivated that needs to be redistributed to other elements. So this is how you can define what percentage of redistribution of forces should take place when you deactivate an element. So I hope up till now you guys have got a clear picture of what age is. Now let's talk about how to model an element which has been casted but the scaffolding will be removed in the next stage. So this is the element where the concrete is still wet. So here we are talking about the cast in situ type of element. So the example that I have taken here is, this is a balanced cantilever bridge again, and these two elements are casted in situ and we still have the scaffolding on CS8. So elements are casted on day 7 of CS8, and in CS9 the scaffolding or the formwork will be removed and the elements will start contributing or taking their own self-weight. So we can follow this methodology. We can model the load of the element and we will not model the element. And when the scaffolding is removed, the load that we modeled for these elements will be deactivated and the element will be activated, and once you activate the element, the self-weight will automatically take care of the weight of the element. So this is how you can do it, and this is the demonstration of how you can define it in Midas Civil. On the left hand side you can see that I have activated the scaffolding and the element load on the day 7 of CS8, and when I come to CS9 I activated the segments and I deactivated the load that I activated in CS8. So as the element appears, the self-weight will be automatically taken into account. So you need to deactivate the pseudo load that you applied in the structure. And this is how you can model the element which has been casted, but you don't want to consider that into the stiffness of the bridge. The second important thing is how to define the composite section for construction stages. As I talked about the composite plate girder bridges earlier, the first stage is installation of the steel section, the second stage is casting of concrete on the top of steel section, and in the third stage the concrete hardens and there is a composite behavior between the steel and the deck on the top. So in Midas Civil that feature is duly implemented. We have a composite section for construction stage dialog box, and here what you can do, you can assign that what part of element will be activated at what stage. So as you can see here, this is a composite section and I have activated the steel part in stage 2, in the stage 1, which is the active stage, and I have activated the deck part in stage 2. So this way I'm telling the program that in stage 1 take only the bare steel section properties for calculating the force effects, and in stage 2 take the composite section properties. Now let me take you to the program and I'll show you some of the features associated with this dialog box. So this dialog box can be accessed through two paths. The first path is you can go to construction stage analysis data and you can define composite section for construction stage, or the shortcut key is this button which is right in front of the stage definition button. Here you can see that this is how it looks like, and here you can select the section which is if it is a composite section it will appear here, and you can define when elements will be activated, as you can see here. If you want to change the stiffness, or if you want to consider or not consider the weight of some of the elements, then you can click on the stiffness option here and you can modify the stiffness by selecting this option, which is stiffness scale. Now sometimes it might happen that you want to model, let's say we are going to model a composite pre-stressed girder bridge. In the first stage we install the girders, we pre-stress the girders, and in the second stage the concrete is casted and it hardened, and now the section is behaving composite with the girders. But the deformation in the girders will be due to the bare girder section and the weight of the concrete, the wet load of the concrete, and that's why we specify the stiffness scale to the weight of the deck on the top of the section as 0, and we do not deactivate the weight, the self weight of the deck that we have defined in the earlier stage. So this is how it is helpful. If you want to take into account the crack section properties of the deck, then you can specify the stiffness change, how the stiffness changes, and the program will take into account the crack section properties. So that was all about the element activation and deactivation in Midas Civil, and I demonstrated how to activate the element in Midas Civil. Now let's talk about the boundary activation and deactivation. So in the boundary activation and deactivation, it's very simple. We need to activate the support or boundary which becomes active in a certain construction stage, and we need to deactivate the temporary support. So as you can see here, this is how the bridge construction is going on, and I applied some temporary supports at this location. So in the program, I can activate the temporary supports at this location in the construction stage, and finally when the temporary support is removed, I can deactivate the temporary support. The flow is same. You need to define the boundary groups first. After you define the boundary group, you can assign the boundary group to the support, and then you can activate the support in a particular construction stage. Now let me take you to the program and I'll show you how to activate and deactivate the boundary. So again we are back to our model. So let's say we want to activate the boundaries in stage 1. So first of all we need to define the boundary. For the definition of boundary, we'll go to model boundary supports, and I'll define the supports at the base of the pier. So I will put them in the group support and I will assign all the supports. So in this way I have defined that the pier support will be activated under the boundary group name support. And now I will add this support in the first stage. So I'll go to the first stage, I'll go to the boundary tab and I will activate the support as you can see here. In this model I have certain elastic links. As you can see, these are the elastic links that I have defined at this location, and I want to activate these elastic links in the first stage. So the method is entirely same. You will go to model boundary elastic links and you will define the elastic link under the boundary group. Let's say elastic link. You will define the elastic links, you will generate the elastic links, and then you will activate the elastic links in the stage. So here I am activating the elastic links, and let's see how the boundaries look like. If I want to see all the boundaries that have been activated in a particular construction stage, I will go to the display tab, I'll go to the boundary tab here, and I will activate all the supports. So I am asking the program that show me all the supports that have been activated or deactivated in this model. So if I go to stage 1, I can see the supports at the bottom of the piers, as you can see here, that I activated just now, and you can also see the elastic links in this stage. So this is how you can activate the boundaries. Now let's take a very hypothetical example that we have some temporary supports in stage 1 at these nodes. So first I will create a boundary group, let's say temp, and I will define the boundary in the Z direction for these nodes, and I will put them in the boundary group temp. Similarly, I'll do the same thing for the nodes at the right end of the bridge. And once I've selected the desired nodes, I will click on apply, and as you can see, the boundary has been defined. Now this boundary will be there only in stage 1. So I will activate the boundary in stage 1, and in stage 2, since it is a temporary boundary, it will be deactivated. So I will go to stage 2 and I will put the temporary boundary in the deactivation list. So let's now see how the boundaries look like. Stage 1, we have the temporary supports, we have the elastic link, and we have the pier support. Stage 2, we removed the temporary supports and we added more segments to the bridge. So this is how you can model any kind of boundary in Midas Civil. The process is again very simple. You need to define the boundary group, define the supports under the boundary group, and then activate or deactivate the boundary group as and when required. Now when you see the boundary tab of the construction stage definition dialog box, you would realize that we have two options. The first option is original and the second option is deformed. Now let me tell you where the original and the deformed option works. So as you can see, this is the description. In the original option, apply the boundary condition to the undeformed position. This is equivalent to imposing forced displacement to the original position prior to defining the supports. It's a lot of words. Let me just tell you through a picture. So in the original position, let's say this is the deformed shape of the structure due to self-weight in this construction state. I want to apply a support. I have two options. Either I can apply the supports here, or I can pull the structure up and then apply the support. And this is equivalent to imposing forced displacement to original position prior to providing supports. Now the question arises, when do we use the original option. The deformed option is pretty much, I think it's intuitive, because as the construction progresses, you create certain supports at the abutments or at other locations based on the deformed shape of the bridge. But let me show you a simple video in which you guys can appreciate how the original supports can be used. So this is the construction methodology of a balanced cantilever bridge, and as you know that the balanced cantilever bridge is pushed in the forward direction. So when the bridge reaches at the pier location which have already been created, the structure will be lifted up, and this is when you need the original option. So again, this is the incrementally launched bridge construction. I am launching the bridge in the forward direction, but the pier has already been constructed. The girder deformed due to the self-weight, so I pulled them up using the jack, and this is where I need the original option. So I hope with video, it has become clearer. Now in certain cases you might need some other type of boundaries, such that as you can see here, in this stage this girder is simply supported at both ends, but when you cast the concrete on the top of it, the girder will become continuous. So for simulating this kind of a behavior, we have an option known as beam and release. You can apply the beam and release at this location, and once the structure becomes continuous, you can deactivate the beam and release, and in this way, in the first stage you will have the simply supported nature of the girder, and in the second stage you will have the two-spin continuous girder thing, because you have deactivated the beam and release. Now let me tell you in the program how you can define the beam and release. The beam and release can be defined under model, boundaries, and beam and release. So you can define the beam and release here. You can put them in the boundary group, and when you want to activate the boundary group, you can activate it, and when the structure has become continuous, then you need to deactivate it. Now let's talk about the load activation and deactivation. The same process is followed for the load also as the process we followed for the structures or the boundary. In the stage 1 or in the step 1, we define the load groups, then we assign the load groups to the load cases, and then we activate the load group in a particular construction stage. So it is pretty much the same philosophy. You need to activate the load, you need to define the load in the certain load groups, and then you activate the load group in certain construction stages. For tendons, as I said before, tendons are activated as loads. We first define the tendon pre-stressing load under a load group, and then we activate the load group when the tendon is installed or pre-stressed. Now let me take you to the program now, and I'll show you how the load is to be activated or deactivated in a particular construction stage. So as you can see in the works tree, I have defined the self-weight, and I put the self-weight in the load group self-weight. Similarly, I have defined the tendon pre-stressed loads, as you can see here, and I have put the tendon pre-stressed loads based on when they are activated. I have put them in certain different load cases. Now let me show you when to activate what load case. So first of all, as we know that as the structure construction progresses, the self-weight will keep on adding. When you define the self-weight using the self-weight feature of Midas Civil, then you don't need to activate it again and again. As the structure is being activated, the self-weight will keep on progressing. So first of all, I will activate the self-weight in stage 1. So I'll go to the load tab. I will activate the self-weight in stage 1, and I want to activate the pre-stressing. So I will activate the desired pre-stressing in this stage, and I will put the wet concrete load and the form traveler load in this stage. So let me show you all the loads that I have activated in this stage. I will go to the load option and I will check on all the loads. So as you can see, when I go to stage 1, we have certain tendons and we have the nodal load. The nodal load is simulating the wet concrete load, as you can see here. Let me change the color of the tendons so that you can see them in a better manner. So here, as you can see, these are the different tendons that I have activated in this stage, and I have activated certain nodal loads. These nodal loads, as I said before, they are simulating the self weight of the cast in situ type of element. So when I go to stage 2, you will see that the load still exists, but the element has been activated. As I said before, when you activate the element, the self weight will be automatically taken into account. For that, I will go to stage 2, and in the load tab, I will deactivate the form traveler load and I will deactivate the wet concrete load. Now when you see stage 1, you will see the load for the form traveler and the wet concrete, but in stage 2, you will see that that load has disappeared. But in this stage, I want to activate more loads because there will be certain more pre-stressing which will be done in the bridge, and the form traveler and the wet concrete load for the subsequent segments must be considered. So for that, I will now define the loads in the second stage. I'll go to the stage definition box again. I'll go to stage 2 and I'll go to the load tab. I will activate the pre-stressing in segment 1 for both the wings of balance cantilever bridge, and I will activate the form traveler 2 load for the second segment and the wet concrete 2 load for the second segment. So let us see what loads have been defined now. Stage 1, we have the tendons in the pier table, and we have the nodal loads which depicts the self weight and the wet concrete load. And in stage 2, the loads that we activated for segment 1 representing the self weight of the element and the form traveler load, they have been deactivated, but we have added new loads which represent the self weight and the form traveler load for the next segment. So this is how you can activate or deactivate the loads to simulate the construction schedule. I hope my audio is clear. We are trying hard to set up the audio here because I can see some of the people have complaints about the audio. I would like to stop at this point and I would like to fix this audio problem first. So those of you who have problems with audio, please write in the questions window and we will stop for a while and we'll try to fix this audio problem. Again, I repeat, if you guys have any problem with the audio, we can first fix the audio and then we can move ahead with the online training. But if you guys are comfortable with the audio, if my audio is proper, then okay, I have got a couple of messages from some people and it seems there is a background noise. But let me just set up my mic here. Let's see what if it changes anything. Did it improve anything? I just plugged in my mic again and I plugged it out. Okay, I got some mixed responses now, so I think it's better to move ahead with the training because you guys, you guys have to invest more time if I just stop in between. So I'll just go ahead with the training. So now let's talk about the different types of load that you define when you define the static loads. Let me go to the program. Let me just deactivate all the loads that you can see here. When you go to the static load cases, you can see that, let's say I want to define a dead load, or let's say I want to define a buried load. Then I can define it in a variety of manner. I can define it as a user defined load type. I can define it as a dead load. I can define it as a construction stage load. Now let me tell you what is the difference between the construction stage load and all other load types. The static loads that are applied as the dead weight can be seen in the construction stages or outside the construction stages in the post-CS. But if you define any weight as a construction stage type load, then you cannot see the effect of that load in the post-CS. So what a post-CS is, I hope you guys are already familiar with the post-CS. In Midas Civil, you can see the construction stage analysis results in different construction stages, and you can also see the results for certain other things like, let's say, response spectrum analysis or moving load analysis in the post-CS. If you define any static load as a construction stage load, it would not appear in the post-CS. We will discuss about it more when we see the results. As we know that the construction of bridge takes place in a finite amount of time, and the creep and shrinkage may play a very significant role by the time. In Midas Civil, we can consider how the creep and shrinkage will affect the analysis. For that, we need to define the creep and shrinkage properties of concrete, as well as we need to define how the elastic modulus of concrete changes with time. So as you can see here, I have laid down the procedure. The procedure is, first define the creep and shrinkage properties and then link it with the material. So we'll do the same thing. We will define the time dependent material property for creep and shrinkage, and then we will link them with the material. So let me go back to the program and I'll show you how to define the time dependent material property in Midas Civil. So when you go to model, you can go to properties and you can go to the time dependent material, creep and shrinkage, and you can define as many properties, as many elements are there in your model. You can define the notational size here, and when you see the creep and shrinkage coefficient, you can just make sure that the creep and shrinkage coefficients that are defined automatically by CBFIP code are in line with your coefficients. So here I have defined the creep and shrinkage properties for grade C4000. Now I'll define the creep and shrinkage properties for grade C5000. As my bridge has two different types of concretes, I'm defining two different types of creep and shrinkage properties. So here we have defined the creep and shrinkage properties for grade C4000 and 5000, and now I'll define how the elastic modulus of concrete changes with time. For that, I will go to time dependent material, compressive strength, and I will define it for grade C4000. I will select the code as CBFIP code. And most importantly, many times I get questions from users that what is the mean compressive strength and how is it different from the characteristic strength. So the mean compressive strength as defined in the CBFIP code, it is not the characteristic compressive strength. It is a bit higher than the characteristic compressive strength, and generally for the Gibbs inch it is 1.16. For Newton per millimeter square, if you are working with the SI units, it's about 8 MPa. So if your strength is 40 MPa, you need to enter 48 here. So when I redraw the graph, you can see this is how the elastic modulus of concrete will change with time. Similarly, I will define the elastic modulus for grade C5000, and I will define it again with the CBFIP code, and this is how it appears. So as of now, if we see the worksheet, you will see that these time dependent properties, they are in blue color. So that means they have not been used. Anything that appears in blue color in the worksheet means they have not been used. They will be used when you link them with the material. So I'll link the properties for grade C4000 with the grade C4000 material, and I will link the properties of grade C5000 with the grade C5000 material. And when you see the worksheet now, it appears black, which means they have been used. So in this way, you can define the time dependent material properties. If you want to define your own creep coefficient, then you can define the creep coefficient for a particular construction stage, and you can assign it as a load group, and when you perform the analysis, that creep coefficient will be used to calculate the creep effects. It can be defined under the construction stage loads. So when you go to load, construction stage loads, you can define the creep coefficient for construction stage, and you can specify your own coefficient. So let's say in the same model, you want to use the CBFIP code, but in a particular construction stage, you want to define your own creep coefficient, then you can specify this creep coefficient and you can activate it in a particular construction stage, and when you see the results, the creep coefficient will be corresponding to this which you have defined here. Now let's talk about the application of creep and shrinkage. Now the creep and shrinkage coefficient for the elements are taken as per the age of activation. So whatever age that you specify when you activate the element, this age, that age will be the age at which the creep coefficient will be taken. And the creep coefficients and the shrinkage values can be seen in the result tables for the construction stage. I'll be talking about this thing in details when I go to the results. Or you can create the out file, and in the text output you can see the creep and shrinkage factors or the coefficients. When you use the CBFIP code or any other code, there are certain factors on which the time dependent material properties are dependent. Now let me take you back to the program and I'll show you when you define the creep and shrinkage. Let's say you want to define it with the CBFIP code. The CBFIP code defines the notational size, which is 2 multiplied by the cross-sectional area divided by the perimeter in contact with the atmosphere, and the creep coefficient is based on this notational size. In AASHTO, it is based on volume to surface ratio. Similarly, in ACI code, it is based on volume to surface ratio. But if you see your model here, it has got different type of sections, and the notational size or the volume to surface ratio will be different for different elements. For that, we have an automated option. You can go to Model, Properties, change Element Dependent Material Property, and you can specify the volume to surface ratio or the notational size automatically. So when I select the auto calculate notational size, it will calculate the notational size, and in this way the notational size has been calculated, and you can verify the notational size by going to the worksheet and right clicking on the change element dependent material property, and this is the notational size for each element. So when Midas Civil will determine the creep coefficient for a particular element, then it will take into account the notational size that has been defined here. So this is how the time dependent material properties can be used while you perform the analysis. Now for the beam elements which have composite section, you cannot define the notational size by this feature, change element dependent material property. For that, you will have to define the notational size when you define the composite section for construction stage. So here you can see H. This H represents the notational size for performing the time-dependent material analysis. And you can calculate that automatically by clicking on this option, Update All H automatically, and the program will take into account the geometry of the section, and it will update all the H automatically. Now a brief description on H, how the H should be described. If you are using a beam element, then the H, the notational size or the volume to surface ratio can calculate it. But if you are using a plate element, then the program cannot automatically calculate the notational size. So for that you will have to define the notational size manually, and this is how the notational size can be defined manually. The area of cross section will be the entire area of cross section of the deck. So let's say this is a deck here, and I have modeled it as a series of solid elements, as you can see. And the notational size will be the area of cross section, which is this cross section, and the perimeter divided by the perimeter in contact with atmosphere multiplied by 2. So this is how you will determine the notational size, and this notational size will be assigned to individual elements, individual solid elements. One more thing, when you model the plate and the solid elements, the local directions of the elements must be aligned for obtaining the correct effect of construction stage, the time dependent materials. So this is the correct alignment, and the X element, the X-axis of the element must coincide with the bridge direction for the plate and the solid elements. Now let's talk about a scenario in which we have the same exact construction for two different portions of the bridge, but after some time they will be connected by a key segment. So as you can see here, the left and the right end of the bridge will have the exact same construction, but they are constructed with a time lag of 100 days, as you can see. So we have two options to model such a construction schedule in Midas Civil. The two options are that first is we start modeling the left segment of the bridge, and once the construction is complete, then we can model the right segment after 100 days, and in this way you can model the actual construction scenario. But the other way is, if you want to cut down your construction stages, you can model both of them individually, but at the time of connecting these two segments together using the key elements, you can activate the time load. Now why should we do that? Because the analysis for segment A and segment B will be exactly same for the number of days they have been constructed, but the only difference will arise when you will connect them together using the key segment. And that's why when I model this type of a bridge in Midas Civil, I will activate this segment and this segment at the same time, but when I connect them together, I will first assign a time load of 100 days to the segment on the right, and then I will activate the key segment. The time load can be activated in the time load for construction stage, which can be obtained under the construction stage loads. So you can define the time load under a load group, and you can activate that time load in a particular construction stage, and when you activate that time load in a particular construction stage, the age of the segment will be increased by 100 days. And this is how the development of concrete strength has to be taken into account. I have already demonstrated that using the model, and this is the procedure how we can do it. Talking about the section stiffness scale factor, let's say you are constructing a bridge in which you have a lot of elements. but you have the pier element, then you have the segments going in different directions if it is a segmentally constructed bridge. Now sometimes it happens that you want to consider the cracked section properties for the piers for performing the analysis, because a major portion of pier can be cracked and you want to modify the stiffness of the bridge as a whole to consider that cracked part for analysis. For that, you can use the section stiffness scale factor. The section stiffness scale factor is available under the section manager of Midas Civil, and you can assign the section stiffness scale factor in a particular boundary group, and then this boundary group can be activated or deactivated as and when required. So let me show you where you can define the stiffness factor, the stiffness scale factor. You go to properties and then you go to the section manager, and when you go stiffness, you can select the section. Once you select the section, you can define the stiffness scale factor and assign them in a particular boundary group. And in this way you can change the stiffness in a particular construction stage. The important part is, let's say you want to specify one more stiffness factor. For that, you should normalize the stiffness, section stiffness first. And by normalizing, I mean that another scale factor which normalizes the stiffness must be activated along with the deactivation of previous scale factor. So let's say we have applied a stiffness scale factor of 0.5 to the IYY, which is the stiffness in the major axis of a section. Now you want to deactivate this factor in a later stage. Then the most obvious approach is just deactivate it and the stiffness will again become 1. But it's not the case. If you deactivate that boundary group for section stiffness scale factor, then the stiffness will remain the same. If you want to increase the stiffness from 0.5 to 1 again, then you will apply a section stiffness scale factor of 2, so that 0.5 multiplied by 2 will become 1 again. So deactivation alone would not help. You need to activate a normalizing scale factor so that the stiffness gets back to the normal. Also in Midas Civil, you can define the effective width scale factor to take into account the effective flange width for the calculation of sectional stresses. You can do that in two different manners. Either you can define it automatically. For automatic definition, we need to follow a certain route and then only you can define it, or you can define it manually in the program. Now let me show you both the options on how we can do that. So if I go to Model, Structure Wizard, PSC Bridge, I can define the stiffness, the effective width scale factor here. So whatever code I want to select, let's say I want to select Astral RFT, I can select the Astral RFT and I can define the effective width scale factor. But once you click on OK here, it will show you an error. The error is no span data has been entered. So the proper route, as I said before, is you will go to Model, Structure Wizard, PSC Bridge, and then you will define the span information. So let's say I don't want to spend my time in defining all the spans. I'll just define them under one span, and I'll define the supports at the ends. And now when I define the effective width scale factor, you can see that the effective width scale factor has been defined. So the proper route is you will first define the span in the PSC bridge, then you will use the effective width scale factor. The second option that you can use is you can define the effective width scale factor as a boundary, and here you can specify the scale factor for IY, or you can specify how the the Z, the distance from the centroid to the top fiber and the bottom fiber will change. So these are the two options that you can use for determination of effective width scale factor. Now the question is, what is the difference between the section stiffness scale factor and the effective width scale factor? If you define the section stiffness scale factor, it will just change the stiffness for performing the analysis. But the effective width scale factor will not change the stiffness, it will just change the stresses. When you calculate the stresses will be calculated as per the effective width. If you want to take into consideration the section stiffness scale factor for calculating the stresses, then you can go to main control data under the analysis field and you can check on this option, consider section stiffness scale factor for stress calculation, and then whatever section stiffness scale factor that you have assigned will be used for stress calculation. Finally, if you want to obtain the force effect due to a particular type of load, then in Midas Civil you can define a dummy stage. Let's say after the 5 construction stages in a particular bridge, I want to see how the thermal effects will affect the bridge. So what I will do, I will first define the 5 stages and I will define a 6th stage which I will say as a dummy stage, and I will define the thermal load and I will activate only the thermal load in that particular construction stage. And when I'll see the thermal effects, I will just see that the force effect of that construction stage, and I will obtain the thermal stresses due to thermal temperature changes in the structure. So the dummy stage is important if you want to see the effect of a particular type of load in Midas Civil. Now let's talk about the construction stage analysis control. When you define and model the construction stages, you have several options that you can choose from to define the construction stage analysis control. The construction stage analysis control can be obtained from analysis, construction stage analysis control. And we have variety of options that you can choose from. So I'll be talking about these options individually. So the first option is to define the final stage. You can either run the model to the final stage. Let's say we have 10 stages in a particular model and I want to run all the 10 stages. Then I can select the final stage as the last stage and the program will perform the analysis till the last stage. Or if you want to perform the analysis only till, let's say, 5 stages, then you can select the final stage as the other stage till stage 5. Now why do we need to do that? Why is there such an option to calculate the analysis only till this stage? The reason is sometimes you want to perform the dynamic analysis in between the construction stages. The dynamic analysis can only be done in the post CS form, and that's why, let's say I want to do the dynamic analysis after 6th construction stage. So I will run the model only till 6th construction stage and then I will define the factors for dynamic analysis and then I will do and obtain the results for dynamic analysis in that stage. There is another option to restart the construction stage analysis. The restart construction stage analysis specifies that, let's say you have 16 stages in a particular model. In this model I have 16 stages and I want to change or modify something in stage 8. So what I can do, I can just ask the program to perform the analysis from 8th stage and I will ask the program to keep the results from stage 1 to 7 to be intact. Because I modified stage 8, so the results of modification in stage 8 will not affect the results in stage 1 through 7. So I don't need to run the analysis again. I can use just this feature and the program will automatically perform the analysis from construction stage 8 and it will combine the results together to give you the final analysis result. When you go to the time dependent effect, you have certain options to choose from. Analysis, construction stage analysis control. You can go to the time dependent effect control, and these are the options that you can choose from. Now let me talk about these options in detail now. So the first option is time dependent effect. Do you want to consider creep and shrinkage or not? Or you want to consider only creep or only shrinkage, or if you want to consider both creep and shrinkage. The second option is the convergence criteria for creep. You can see that since creep is analyzed using iterations, you can specify what are the different number of iterations that you want to do and what is the tolerance. The third option is use only user's creep coefficient. As I said in the load definition, that you can specify a creep coefficient by yourself, and in this method Midas Civil will use only the creep coefficient that has been defined for you for performing the time dependent material analysis. The internal time step for creep is important when the duration of stage is very high. Sometimes you want to obtain what is the effect of creep after 70 years. For that, what you can do, you can define a stage having 70 years as the duration, and the program will calculate the creep effect after 70 years. Now how the program does that? Program divides the stage automatically into certain smaller stages, and then it obtains the creep effect. The steps will only be used for analysis internally in the program, and the results cannot be seen for those steps. But let's say you want to see how the creep is affecting the structure after 1 year, 2 year, 5 year, 10 year, 20 year, then you can create certain additional steps in your construction stage, and you can ask the program to save the result for all those additional steps, and you can obtain the creep effect in different individual steps for the last stage to obtain the creep effect in 1 year, 2 year, 3 year, 5 year or 10 year. Then we have a tendon tension loss effect. It is checked on to reflect the effect of pre-stressing tension loss of tendons due to creep and shrinkage. If you want to consider rebar confinement effect for creep and shrinkage, you can check on this option. If you want to apply the time dependent effect elastic modulus to post CS, then you can use this option. As we know that the concrete gains strength in 28 days, and let's say you constructed the bridge and the bridge construction takes place only in 15 days. I'm just giving a very hypothetical example, and you want to consider the elastic modulus of concrete that you obtained after 15 days for performing the analysis, then you can check on this option. When you check on this option, the elastic modulus that the concrete has after 15 days will be taken into account for performing the analysis for the moving loads or any other load effect in the post CS. Finally, the tendon tension loss effect due to elastic shortening. It is checked on to reflect the pre-stressing tension loss of tendons due to the elastic deformation of concrete due to loads other than pre-stressing loads. Then we have an option for P delta effect. In Midas Civil, you have two different options for P delta analysis. The first option is you can go to analysis and you can check on P delta control. This P delta analysis will only affect the post CS mode. That is, when you perform the final stage analysis in the post CS, then only this will help. But if you want to perform the P delta analysis in individual construction stages, then you need to check on this option, include P delta effect only in construction stages. So if you want to consider the P delta effect in construction stages, you can do that by checking on this option. The second option can be that you want to distinguish some load cases from dead load so that you can see their effect. Let's say I want to see what additional moments are created by the form traveler while I'm constructing the bridge. So you can put the load case of form traveler in this option, and when the program will show you the results, there will be two different options. The first option will be CS dead load, and the second option will be CS erection load. And if you put any load case in this option here, it will appear only inside the erection load and not inside the dead load. So again, if I go to analysis, construction stage analysis control, if I put the form traveler inside the load case to be distinguished from dead load for CS output, then the form traveler load will appear under the erection load and not under the dead load. Then we have one more option here, which is the initial force control. The member forces of the last step of the last construction stage in the construction stage analysis are converted into the initial force for geometric stiffness to reflect the forces into the geometric stiffness of the structure at the post-construction stage. So let's say you are modeling a cable stayed bridge in Midas Civil, but in cable stayed bridge you will activate the pre-tension load in the cables in certain construction stages. But when you want to perform the moving load analysis, those pre-tension loads should be considered. And if you check on this option, the final stage pre-tension loads in the cable will be used to determine the geometric stiffness of the cable for performing the analysis for the moving loads. As we know that the cable elements, the pre-tension in the cable element will determine the stiffness of the cable. This factor or this option is relatively very important. Again, we have one more option to apply the initial member force to construction stage. If we apply initial member force to construction stage is checked on, then the final member forces of the last construction stage will be applied to the post construction stage, and it is again to determine the geometric stiffness if you are performing the dynamic analysis or the geometric nonlinear analysis. Then we have one more option, the initial tangent displacement for erected structures. Now let me tell you what it means by initial tangent displacement. I think it is better demonstrated using this picture. As you can see here, I have to add more segments on the left end and the right end of this bridge. Now due to the self-weight, this structure has already deformed. If I add new segments, they will have a induced deformation without even, they will have, when you will install them due to the rotation of node at this location, their installation direction will be this. And when you check on this option, initial tangent displacement for erected structure, it will automatically tell you what is the initial tangent displacement for the new segment. Then there is an option for stress decrease at the lead length zone. You can select a method of computing stresses over the transfer length in a post-tension model. So if the model is the bridge that you have modeled is post-tension, if you want to consider how the stress is transferred, because as we know that at the ends the stress is lower, and as we move towards the mid of the tendon the stress increases, and you can take into account this feature by checking on this option. Either you can include a constant stress in the lead length zone, or you can increase it by using linear interpolation. Now if you have defined tendons inside a section, the section properties are bound to change, because let's talk about the post-tension structures in which we first create the duct and then we install the tendons. Now because of the ducts, the section properties of the section changes. If you want the section properties of the section to change with the definition of ducts or the definition of tendon, then you can check on this option that the beam section properties should change with tendon. The final option is the save output for current stage or step. What this option does is it will save the result for individual construction stage so that you can see what is the result in a particular construction stage. So let's say I activated a certain type of load in a construction stage and I want to see the effect of only that load. Then I can check on the option current stage displacement or force to see the effect of only the load that has been activated in that stage. So finally, we have two options for saving the results for construction stages. The first option is save result as stage, and the second option is you can save the result for additional steps if you have any. Now let's talk about the construction stage analysis results in depth. So as you can see here, in Midas Civil you obtain the construction stage results in a variety of manners. You obtain the dead load result, the erection load result, the tendon primary, which is the primary effect of tendon result, the secondary effect of tendon, the primary effect of creep, the secondary effect of creep, the primary effect of shrinkage, and the secondary effect of shrinkage, and then you can obtain the summation of these all. Now let me first tell you about what this erection load will give you and what this dead load will give you. If I go to this model, let me open an analyzed model in front of you so that I can show you the result features. So this is an analyzed model. It depicts the construction stages of the model that we have just modeled. So here if I go to the beam forces, I have these options, the dead load, erection load, etc. Now let me talk about dead and erection load first. You can see that in this bridge I have defined self-weight, pre-stress load, form traveler load, wet concrete load, and there are certain other loads that we have defined. All the load that you will define, which is like a dead load to the structure, its result will appear under CS dead load. So here in the CS dead load, the self-weight results, the form traveler result, the wet concrete result, and the other forces result will be obtained under the CS dead load. But if you put a load case under, let me change the mode. If you put the load case under, let's say I put the load case form traveler under this load case to be distinguished from the dead load for CS, then the program will show you the result for this force in CS erection load. So here if I put the form traveler in that option, we can see the result of form traveler in this erection load. If I want to see the effect of the loads activated in this particular step, then we can check on this option and we will see the effect of loads activated in this stage only. Now let me talk about how the results are obtained in Midas Civil for the construction stage analysis. As you can see here, the results, the deformation results, the stresses, the bending moment diagrams, etc. are accumulated. That is, you take the result of previous stage and then you add the result of the current stage force and then you give the result for this stage. So as you can see here, the default results obtained for construction stage analysis are accumulated results. That is, if we check the deformation due to dead load for CS2, it would be the deformation for CS1 plus the deformation obtained due to the dead loads in CS2. The current step deformations are obtained by applying the current step force function to the structure. Now let me take you to the program and I'll show you how the deformations are obtained. So if I go to result, deformation, deformed shape, if I select the dead load, this is how the deformed shape looks like, which is just the accumulated results. If I want to obtain the actual results, I need to activate this option. Okay, so when I obtain the results the deformation results in default mode, it will be just the accumulated results. So when you see the randomness in this deformation, it is because it has been obtained due to the accumulated deformation. You can see certain breaks here. If you want to obtain the real deformation, then you need to check on this option, stage step real displacement, and this option will take into account the initial tangent displacement of the new elements that have been created. Now let me talk about the weirdness of this deformation. Why is it weird? So as you can see, this node and this node which I have highlighted, they are activated in this particular construction stage, and that's why they are higher than other nodes, because the other nodes have already been deformed due to self-weight and all other force effects, but this node has not been deformed. It is an accumulated deformation. The deformation of this node before this construction stage is 0, and in this construction stage there will be slight deformation, and that's why it is higher than all other nodes. But this is not going to be the picture in the reality. In reality, as I said before, the initial tangent displacement will bring this node further down, and it will have the z direction displacement much more than all other nodes. If you want to obtain that feature, then you can check on this option, stage step real displacement, which will show you the real displacement of this structure. For obtaining this option, we need to activate this force. Let me just quickly analyze it, and I'll show you the results. In the meantime, let me go back to the presentation. So I hope you understand that in Midas Civil, the results, the deformation result, the force effects, they are all accumulated. So when you see the deformation at CS10, it will be the deformation at CS9 plus the deformation due to all the loads in CS10. Now let me talk about this option. As I said before, you can check on the option initial tangent displacement in Midas Civil, and then you can obtain the stage step real displacement. Now let me tell you what it does. Let's say I have a simple cantilever beam that has been created in 3 different construction stages. Now what will happen? Due to the first construction stage, there will be a deformation in girder 1 due to self-weight. When you activate the second part of the cantilever beam, when you construct the second part of the cantilever beam, because of the rotation of the node here, it will have an inherent deformation and a deformation due to its self-weight. And similarly, the same will be the case for the third segment. So the third segment will have inherent deformation delta 31 due to the deformation of rotation of node at this location. It will have an inherent deformation delta 32, which will be due to the rotation of this node, and due to its own self-weight there will be a more deformation, and the net displacement will be the summation of all of them. And this is what the stage step real displacement option does. So we will activate the initial tangent displacement, and when we activate the initial tangent displacement and when we run the analysis, we will obtain the stage step real displacement in our structure, and this displacement will be the actual deformation of the structure in the field. So let me go to the deformations now. Now I'll show you the deformation in stage 4. Now this is the dead load deformation, If I activate the stage step real displacement, this is the actual deformation that you expect on the ground. So if I uncheck this option, this is the accumulated deformation, which is weird because it is activated and this node was not there in the initial stage. So the deformation in the previous stage was 0, but in this stage it will have certain deformation due to its own self-weight, the self-weight of the element it has been attached to. But when I check on this option, it is the real displacement at this stage. If you just want to obtain what is the displacement due to the loads activated in CS4, you can check on this option, current displacement, current step displacement, and then this is the displacement obtained due to the forces activated only in this construction stage. So I hope now you got to know what is the difference between the default deformation, the deformation with stage step real displacement checked on, and the deformation with current step displacement checked on. In the field, you expect to obtain the deformation that is obtained by stage step real displacement. Again, the force effects are the same. The force effects are again accumulated. If you want to obtain the bending moment in construction stage 10, it will be the bending moment in construction stage 9 plus the current step bending moment in construction stage 10. For that, you can go to the force effects. You can select the beam diagrams. For dead load, this is the bending moment. And if you want to obtain the bending moment due to the force activated in CS4, you can check on this option, current step force, and this is the bending moment due to the load activated only in this stage. The verification can be accumulated bending moment is equal to the bending moment at the previous stage and the current step bending moment at this stage. Similarly, the same story is with the stresses. You can check the stresses for individual construction steps and it will be accumulated again. If you want to obtain the stresses for different parts in a composite section, then you can select the part 1 or the part 2. So here, if I go to stresses, if I go to beam stresses, I can select the part 1 and part 2 here. For this model, we don't have the composite section, that's why the total appears. But if we have a composite section in which we have 2 or 3 parts, then we can select the part 1, we can see the force effects on part 1 or the stresses on the part 1. Similarly for part 2, and if we want to obtain the summation, then we can go for total. The tendon time dependent loss graph can be obtained from the model. You can obtain the graphical result or you can obtain the tabular result. Let me show you how you can obtain the graphical or tabular result. The graphical result can be obtained from tendon time dependent loss graph. This is how it looks like. When you change the stage, you can see that the tendon force is going down because of losses. But if you want to obtain the individual losses, then you can go to result tables, tendon loss, and you can select the stage in which you want to see the loss, and you can see the loss individually for elastic deformation, creep and shrinkage, relaxation, etc. Now to give you an idea, for pre-tension and post-tension, the calculation of loss is different as we know. The friction loss is not calculated for pre-tension, but for post-tension it is calculated. Similarly, anchorage slip loss will be calculated for post-tension only. Elastic shortening loss will be calculated only for pre-tension. The creep and shrinkage will be calculated for both pre-tension and post-tension, and the relaxation loss will be calculated for both pre-tension and post-tension. And this is how the table that we obtained looks like. The first column is the stress in the tendon after instantaneous loss, which can be elastic deformation loss in pre-tension tendons. In post-tension, it can be friction loss. The and these are the equations that we use for anchorage loss and friction loss. For details, you can go to the analysis manual. The elastic deformation loss B is the elastic deformation due to the additional loads, or if you have activated another tendon after you activated a tendon in a previous stage, then elastic deformation loss can occur. For an example here, there are two tendons, tendon 1 and tendon 2. I activated or I pre-stressed the first tendon in stage 1, and in stage 2 I pre-stressed the second tendon. Now due to the pre-stressing of second tendon, there will be an inherent elastic deformation loss in the first tendon, and in Midas Civil you can obtain this loss under elastic deformation loss B. Also, other type of elastic shortening losses which are caused by subsequent loading such as self-weight, live loads, creep and shrinkage, etc. after the pre-stressing force is applied are included in this elastic deformation loss. Due to creep and shrinkage, they can be obtained on the column of creep and shrinkage. The relaxation loss can be obtained on the column of relaxation loss. And for CBFIP, this is how we calculate the relaxation loss. The initial stress is multiplied by the final loss ratio due to steel relaxation, and the progression of steel relaxation is taken into account when we calculate the final loss. If you want to calculate or obtain the graphs in Midas Civil, then you can either go for bridge girder diagrams in the post-construction stage, or in the construction stage you can see the stage history graph. The stage history graph can be obtained under step stage history graph. You can define a function. Let's say I want to see the deformation of this node in the z direction. Then I can create a graph. It appears here, and I can select what do I want to see in the x-axis, the time or the day or the different stages, and I can see for what load case do I want to see the result. When I click on graph, this is how it appears. You can see that the displacement goes down with time. Similarly, if you want to obtain the graph for the bending moment, just create a new function, select beam force here, create a new function, select the element where you want to obtain the force, select the type of force you want to obtain, and check on this, obtain due to dead load, and this is how the bending moment looks like. So it becomes more and more negative as the new segments are added. You can check the element properties at each construction stage. As I said before during the modeling of creep and shrinkage properties, I said that you can check the creep and shrinkage properties, and they can be checked at the result tables for construction stages. You can go to result tables, construction stage, and you can check the element properties at each stage, and it will give you the creep coefficient and the shrinkage, cumulative shrinkage strain. Also, it will give you the start elasticity and the end elasticity. You can see how the elasticity changes with different stages, and you can make a check whether the program is performing the analysis or taking into account the correct elasticity. If you want to obtain the results in the tabular format, then you need to activate the elements for which you want to see the results. For that, you have two options. You can either obtain the tables by going into the beam diagrams, right clicking on this option, and then you can activate the elements where you want to obtain the tables, and you can activate for which construction stage or the step you want to obtain the table. So here I have obtained the table for step 1 in CS4 and the last step. So we have the first step, middle step, and the last step in construction stage 4. If I want to change the stage or the elements, anything, I can just go to activate records. Let's say I want to see the effect of tendon primary, then I can see the effect of tendon primary. I can change the stage or the step, and this is how I can obtain the results due to the tendon primary in certain elements in different construction stages. The second option is you can go to result tables and you can go to respective table, whatever table you want. If you want to obtain the force in the elastic link or the bearings, you can go for elastic link. In the beam, you can go to beam and you can go to beam force and stress. So after you go to the result tables, you can obtain the tables for anything, but it's gonna yield you the same thing. You will get the same dialog box and you will have to activate or deactivate or add the stage or the load case in this dialog box. If you want to create the load combination, we have different options. You can create the load combinations automatically in Midas 7 by going into result combinations, and once you check on auto combination, let's say I want to select Astro LRFT 2011, sorry, Astro LRFT 2007, then I have three options. Either I can put in only the static loads, which are the loads that are defined as static loads, or the construction stage loads, or static plus construction stage loads. So when I select this type of option, the program will automatically consider that these are the different loads that are construction stage loads, and the different factor will be applied. So in this way you can define the construction or the load combination for the construction stages. I forgot to mention that in Midas Civil, when you perform the analysis, you have the results for all the construction stages and the post CS. The post CS is the one where the moving load analysis, response spectrum analysis, or all other kind of dynamic analysis are being done. And in this way you can obtain the results in Midas Civil. So this concludes the session for today, the training session for the construction stage analysis. It was more of an informative session than the step-by-step tutorial, because I had already modeled the bridge. I just wanted to show you how to model the construction stages, and I hope I was able to convey my message to you guys. If you guys have any question, I'll be more than happy to answer any of your question if you write the question in the questions window.